Good afternoon, one and all. Myself, Deepak Jadhav from Department of Mathematics, Smt.CHMCollege. I am an assistant professor in the department, working from since last 10 years. Today, we are here to listen T.Y.B.Sc Mathematics Paper 1, Semester 5, Unit number 1, that is Multiple Integrals. Am I audible?
Yes, sir.
Okay. So, I may require some confirmations in between. So, please give me some confirmations, like
Yes, yes,
whether
yes,
my
sir.
screen is there always and I'm audible. Okay.
Yes, yes, no problem.
So, topic of my today's talk is sketching of regions in R2 and describing regions in R2. The unit number 1 in multiple integrals is nothing but basically devoted to study of double integrals and triple integrals. I hope the students are from T.Y.B.Sc Mathematics same part, regular students. So today in this talk, we are going to study sketching of bounded regions in R2 and describing the regions. This is the first part that I would like to cover. The second part that I would like to cover is sketching solid regions in R3 and describing them. This is the second topic that I would like to cover in this 1 hour session. And if time permits, we would like to go for a mathematical open source software, that is FOSS, free and open source software, Geogebra, which is basically for plotting curves in R2 and plotting surfaces in R3. So this is my plan for today's talk. We'll like to do first of all in R2, then we'll like to do in R3, and then finally we'll like to see mathematical software, that is GeoGebra. Okay, so double integrals. Why do we require double integrals? Is suppose if I have a function from a bounded subset of R2 to R. Suppose if I have a function D is a bounded subset of R2 and F is the function defined on D, and it's a bounded function then I would like to know, is it possible to integrate F over D? So in this case, since the domain of this function is a subset of R2, so what we will get is nothing but double integral. And the notation for this you may have already seen in your course, that is double integral of F dA over D. So it has a very good, nice and detailed definition, like one has to go for the partition of this domain. First of all, you have to enclose this domain in a rectangular domain, in a closed and bounded rectangle, subdivide that rectangular domain into small subrectangles. Then that means consider partition of this rectangular domain. And then you have to consider upper Riemann sum, lower Riemann sum. Then you have to refine the partition. Then you have to take the supremum of all lower Riemann sums and infimum of all upper Riemann sums. So that is compute UF and compute LF. If these two are equal, then we say F is double integrable over D. And the common value of these two is nothing but the value of double integral of F dA over D. That is the definition of double integral of F dA over D. So I hope you have already studied this definition. In this lecture, what we are going to see is how to evaluate this kind of double integral. How to evaluate this kind of double integral. It's not always possible to apply the definition for evaluation of this double integral. So we come across a very strong statement in case of multiple integrals, that is Fibonacci theorem. This theorem provides us a way for the evaluation of double integral for the bounded function over the domain D. I hope that this statement is also studied, or if it is not, let us state the statement. Statement goes like this. Let capital R is equal to AB cross CD be a rectangular domain in R2. Let f from R to R be a continuous function. Then f is double integrable over R. Moreover, we have double integral of f dA over d, double integral of f dA over R is equal to, the Fibonacci theorem says that if your function is continuous, then it is double integrable, and moreover, it provides us a tool, efficient tool to compute this double integral. It says that this double integral is equal to limit x from a to b and y from c to d fxy. Since inner integral has got limits of y, I'm going to integrate with respect to y first and then with respect to x. It is also same as limit from y to y from c to d and x from a to b fxy dx dy. So the integrals on the right hand side, these are called as iterated integrals. Integrals on the right hand side are called as iterated integrals. And Fibonacci theorem says that these iterated integrals are always exist if your function is continuous. These iterated integrals are always exist and they are equal. They are equal. And the common value of these two, the value of these two is exactly same as the value of double integral of f dA over R. So there is no need of going through the whole definition to compute this. Once you know the Fibonacci theorem, then for the computation of this double integral, we just have to use the iterated integrals. And we have to compute any one of these two. And we have the answer in our hand. So this is the Fibonacci theorem standard form. This is the Fibonacci theorem standard form. Can I clear the board?
Yes, sir.
Okay. So this theorem is applicable to rectangular domains. Moreover, the standard rectangular domains like this. This is closed interval A, B, and this is closed interval C, comma D. If your rectangular domain, it's a standard rectangular domain, then we have standard form of Fibonacci theorem. Standard form of Fibonacci theorem. But every time we are not so lucky that our domain is always a standard rectangular domain. Very soon we may offer come across the domains which are not standard rectangular domain, but they are any arbitrary bounded domains like this, like D. Then I need a stronger or slightly general version of Fibonacci theorem. General version of Fibonacci theorem. So general version of Fibonacci theorem also exists, but to use that Fibonacci theorem, one should know that the domain D, which is a bounded subset of R2, how to express that domain D, how to sketch that domain D, how to find limits of X and Y for that domain D. Once you have the limits of X and Y for that domain D, then we can apply the general version of Fibonacci theorem and we can evaluate the corresponding double integral. So in today's talk, we are going to study how to sketch and describe the bounded domains in R2. Okay, so to start with, R2 is a Cartesian plane, x-axis, y-axis, both are intersecting 0 of each other and they are perpendicular to each other. They divide the full plane into 4 quadrants: first quadrant, second quadrant, third quadrant, and fourth quadrant. Okay, so what are the objects that we have studied in R2? They lies in R2. So first of them is a straight line. I hope all of you know the equation of straight line. That's nothing but ax plus by plus c is equal to 0. I prefer the another form of equation for the straight line that looks like this: x by a plus y by b is equal to 1. That's a double intercept form. So by looking towards this equation, in just an instance, I can say this equation intersects x-axis at a comma 0 and intersects y-axis at 0 comma b. So I just have to locate these 2 points. This is on x-axis and this is on y-axis, and I have to connect them by a straight line. That's it. This is the graph of that straight line. This is the graph of that straight line. So first important object in R2 is straight line. And the equation for the straight line is this. Okay. So next important object in R2 is parabola. So there are 4 standard equations of parabola. Let us look at them one by one. First of them is equal to y equal to x square. So how does the graph of this equation looks like? Let's observe that. Y equal to x square. So there is a square of x and power of y is 1. Linear. This equation is linear in y and quadratic in x. So whether it is plus x or whether it is minus x, the value of y remains the same. Value of y remains the same. So that says these 2 points, both the points lies on the graph of this equation because both the points satisfy the same equation. Plus x comma y, if it lies here, minus x comma y is exactly mirror image of this point about y-axis. So it will be somewhere here. And this is true for all the points. This is true for all the points. So locus of all these points is like this. Locus of all these points is like this. And this is called as parabola. This is called as upward parabola. This is called as upward parabola. So equation y equal to x square, when we try to sketch in R2, it looks like this. The slight variant of this equation is y is equal to minus of x square. X-axis, y-axis, origin. So graph of this equation looks like this. Y equal to minus of x square is called as downward parabola. Is called as downward parabola. Is it okay?
Yes, sir.
Okay. The other 2 standard equations for the parabola are x equal to y square and x equal to minus of y square. So x equal to y square this equation, you may have studied in 12th standard. It is a parabola opening on right hand side. Parabola opening on right hand side. And about this equation is exactly mirror image of this about y-axis. This is opening on left hand side. Opening on LHS, left hand side. So these are the four standard equations of parabola. Y equal to x square, y equal to minus x square, x equal to y square, and x equal to minus of y square. The next important object in R2 is ellipse, or before that, circle. I hope the equation of circle is known to all of you. It's nothing but x square plus y square is equal to r square. This is the equation of standard circle. Center of the circle is 0, 0 and radius is r. So when we try to graph equation of the circle, it will look like this with radius r. Centered at 0, 0 and radius r. A general equation to this looks like of this form: x minus h whole square plus y minus k whole square equal to r square. So graph of this equation, the center of the circle is shifted to h comma k. Radius is still r. X axis, y axis. Origin. Next object, important object, is ellipse. Equation of ellipse in R2 is x square by y square plus y square by b square equal to 1. Depending on a and b, the shape of ellipse looks like this. If a is greater than b, and shape of ellipse will look like this. If a is less than b. Equation is same, x square by a square plus y. Equation for both the graphs is same. Depending on value of a and b. If a is greater than b, it looks like a horizontal ellipse. If a is less than b, then it looks like a vertical ellipse. Next equation or next object is nothing but hyperbola, whose equation is x square by y a square minus y square by b square is equal to 1, and its graph looks like this. It's very familiar graph. The another variant of hyperbola equation looks like this: xy equal to constant c. So depending on constant, we have the graph. If c is greater than 0, then graph lies in first and third quadrant. Sorry. If c is greater than 0, then graph lies in first and third quadrant. So this is the graph of hyperbola, whose equation is this: xy equal to c, where c is a constant. If c is greater than 0, it lies in first and third quadrant. The graph, as x is approaching towards 0, graph is going close and close to y-axis, but it will never intersect y-axis. Same way, as x going towards infinity, the graph is going close and close to x-axis, but it will never intersect x-axis. If c is less than 0, then graph lies in second and fourth quadrant. If c is less than 0, then graph lies in second and fourth quadrant. These are the some standard equations of the curves one should know when we study double integrals. Now, there is some bounded region and I want to describe this. D is bounded region in R2 and we want to describe that region. We want to describe that region. So describing a region means finding limits for x and y so that the region represented by those limits. So let's look at one example. D is bounded by the line x plus y equal to 1 with coordinate axis. So I want to describe this region. I want to describe this region. So first and important step is you should able to plot the region. You should able to plot the region. All the equations which are given in the problem that you should able to plot. So if you read the problem carefully, there is only one equation given, x plus y equal to 1. So it's a linear equation in two variables. So that represents a straight line. So if you observe, if you compare this equation with this, x by a plus y by b equal to 1, we have the value of a is also 1 and value of b is also 1. That means x intercept of this line is 1, 0 and y intercept of this line is also 0, 1. So we just have to locate these 2 points and we have to connect them by a straight line. So this is the graph of x plus y equal to 1. The problem also says about coordinate axis. D is a region bounded by the line x plus y equal to 1 with coordinate axis. So there are coordinate axes which are already there, x axis and y axis. So once you have plotted the region, the next step is you should able to identify the region. You should able to identify the region. So this is the region D, which is stated in the problem. So once you have identified the region, next step is to describe the region. So when it comes to describing a region, that means I need expression like this. D is equal to collection of all ordered pairs x, y belonging to R2 such that something less than equal to x less than equal to something, something less than equal to y less than equal to something. That is what I have to find out. Limits for x and y, limits for x and limits for y. More specifically, lower limit for x, upper limit for x and lower limit for y and upper limit for y. So that this all points will lie inside the region D. So since there are two variables x and y, I have a choice in the sense whether to choose constant limits for x or whether to choose constant limits for y. So depending on this choice, we have two descriptions for the region. One of the description we call it as type 1 description and another description we call it as type 2 description. So we have two descriptions, type 1 and type 2 descriptions. So in type 1 description, we have limits of x are constant. And in type 2 description, we have limits of y are constant. So suppose I want to describe this region D as a type 1 description. I want to describe this region D as a type 1 description. Then I want to find constant limits of x. Type 1 description means constant limits for x. So x-axis is the horizontal axis. X-axis is the horizontal axis. So observe your region horizontally. Observe your region horizontally. Yes, this is a region. That's triangle, bounded triangle, right angle triangle. That's the region. So find the leftmost extreme point of the region horizontally. So any point on this y-axis is the leftmost extreme point of the region. This is the extreme left of the region. What is the value of x for this extreme left? So that's 0. So 0 less than or equal to x. So lower limit for x is 0. So how we have computed the lower limit for x? We have observed the region horizontally and we have finded out the leftmost extreme point of the region. So leftmost extreme point of the region lies on y-axis, for which the value of x is 0. So 0 is a lower limit for x. 0 is a lower limit for x. Now to find upper limit for x, locate the rightmost extreme of the region. Rightmost extreme. So this point is the rightmost extreme point of the region. After this point, there is no region on its right. Whole region lies on the left of this point, and this is the rightmost extreme point of the region. What are the coordinates of this point? Coordinates of this points are 1, 0. What is the value of x for this point? Value of x for this point is 1. So upper limit for x is 1. Upper limit for x is 1. These are the constant limits of x. This is how we have to find constant limits for x. Let me repeat. X-axis is a horizontal axis. Observe your region horizontally. Find leftmost extreme point of the region and rightmost extreme point of the region. From the leftmost extreme point of the region, its x coordinate is a lower limit for x. From the rightmost extreme point of the region, its x coordinate is the upper limit for x. This is how we have to find constant limits for x. And now we have to find limits of y. So to find limits of y, first of all, observe your y-axis. Y-axis is the vertical axis. So shade your region by drawing vertical arrows, which are pointing upwards. Shade your region by drawing vertical arrows which are pointing upwards. The direction is upward. We have drawn arrows parallel to y-axis to find limit for y. So to get the lower limit for y, observe initial point of all the arrows. So these are the initial point of all the arrows. Where are they lying? They are lying on x-axis. What is the equation of x-axis? Y equal to 0. What is the value of y? 0. So that's a lower limit for y. That's a lower limit for y. Once again, to find lower limit of y, you have to observe initial point of all the arrows. Find the equation of a curve on which those initial point lies. In this case, it is x-axis. Find equation of that curve, that's y equal to 0. The value of y is a lower limit for y. For the upper limit of y, observe final point of all the arrows. These are the final point, tips of all the arrows. Where are they lying? They are lying on this line. What is the equation of this line? X plus y equal to 1. हम किसका limit find out कर रहे हैं? We are finding limits of y. Solve this equation for a value of y. So from this equation, value of y is 1 minus x. So this is the upper limit for y. This is the upper limit for y. So D is collection of all ordered pairs x comma y belonging to R2 such that 0 less than or equal to x less than or equal to 1 and 0 less than or equal to y less than or equal to 1 minus x. So this is a type 1 description for the region D. This is type 1 description for the region D. Now, let's look at the same region, but this time we'll go for type 2 description. So same line, x plus y equal to 1. This is 1, 0. This is 0, 1. And this is the region D. So type 1 description was D is a collection of all ordered pairs belonging to R2 such that 0 less than equal to x less than equal to 1, 0 less than equal to y less than equal to 1 minus x. That was a type 1 description. Now let's go for type 2 description. Type 2 description means y variable will receive constant limits. So we will find limits of y first. We will find limits of y first, and those are constant limits. So how does y-axis looks like? Y-axis is the vertical axis. Y-axis is the vertical axis. So observe your region vertically. Observe your region vertically. Find out the bottommost point of the region. So this is the bottommost part of the region, which lies on x-axis. What is the value of y for this? 0. So 0 less than or equal to y. Then find the topmost point of the region. Observe your region vertically. Find topmost point of the region. So topmost point of the region is this 0, 1. What is the value of y for this? 1. So that's the upper limit for y. Once you are done with this, so that will, in this way, you can achieve lower and upper limit for y. Now for limits of x, next task is I want to find limits of x. So how I'm going to do is observe x-axis. X-axis is the horizontal axis. So draw horizontal arrows. Draw horizontal arrows, which are pointing from left to right. The direction is from left to right. Observe their initial point. These are the initial point of all the arrows. Where are they lying? They are lying on y-axis. What is the value of x for that? 0. So 0 less than or equal to x, less than or equal to. For upper limit of x, observe the tips of all the arrows. Observe the tips of all the arrows. These are the tips. Where are they lying? They are lying on the line x plus y equal to 1. What is the value of x from this equation? 1 minus y. So that's the upper limit for y. That's the upper limit for y. So this is a type 2 description for the same region. This is a type 2 description for the same region. This is type 1. This is type 2. Observe the difference. Here x has got constant limits. Here y has got constant limits. That's the difference. That's the difference between type 1 description and type 2 description. Let's look at one more example. That is, D is region bounded by y equal to x square and y equal to x. D is a region bounded by y equal to x square and y equal to x. Okay, so first step is plot all the curves. First step is plot all the curves. So there are only two equations given in the problem. Y equal to x square and y equal to x. So we have already seen this equation is the equation of parabola and this is a straight line. Linear equation in two variable is always a straight line. So this is a parabola. So if we recollect, it's an upward parabola like this. Y equal to x square. So upward parabola like this. X-axis, y-axis. Y equal to x. That's a straight line passing through origin. It is like this. Y equal to x. Y equal to x. So luckily we have got only one bounded region. That's this. And the problem also says D is the region bounded by y equal to x square and y equal to x. So this is y equal to x square and this is y equal to x. So this is my region D. This is my region D. So observe these two curves intersect at two different points. One is here and another is here. So first step is calculate all the intersection points. So this coordinates of this point are not known to us. That's 0, 0. But what about this intersection point? So we have to find coordinates of this intersection points first. For that, we have to solve these two equations simultaneously. So let's solve. Substitute value of y equal to x here. So you will have x square equal to x. So x square minus x equal to 0. X into x minus 1 equal to 0. Thus that says x is equal to 0 or x is equal to 1. If x is equal to 0, will imply y also 0. If x is equal to 1, will imply y also 1. So we have 2 points of intersection. One is 0, 0 and another is 1, 1. So there are 2 points. One is origin, which is already there. We know already they intersect at origin. Another point is here. So what are the coordinates of this point? 1, 1. Now, let's go for describing this region. So suppose I want type 1 description. Capital D is collection of all ordered pairs x, y belonging to R2 such that type 1 description means x variable is going to receive constant limits. So observe your region horizontally. Observe your region horizontally. So find the leftmost extreme point of the region and rightmost extreme point of the region. So this is the leftmost extreme point of the region and this is the rightmost extreme point of the region. Your region lies between these 2 points. Its x coordinate lies between these 2 points. On the left of this, there is no region. On the right of this, there is no region. Our region lies between these 2 points. Their x coordinate. So what is the value of x for this point? 0. So 0 less than or equal to x, less than or equal to. What is the value of x for this point? That's 1. So that's the upper limit. So to find constant limits of x, we have observed our region horizontally, and the leftmost extreme point of the region will give me lower limit for x, and the rightmost extreme point of the region will give me upper limit of x. Once you are done with this, then we have to draw vertical arrows within the region pointing upwards like this. To get the lower limit of y, observe their initial point. Where are they? Their initial point lies on a parabola. What is the equation of parabola? Y equal to x square. What is the value of y? X square. So that's the lower limit for y. X square less than or equal to y. Less than or equal to. Observe their tips for the final limit of y. Observe the final points, tips of all those. Where are they? Where are they lying? They are lying on y equal to x line. What is the value of y? X. So this is the upper limit for y. This is the upper limit for y. So this is a type 1 description for the region where x has got constant limits and y has got variable limits. Now the same region but type 2 description. This is y equal to x square. This is y equal to x. This point is 1, 1, x-axis, origin, y-axis. This is your region D, which I want to describe. But this time type 2 description. So D is equal to all x comma y belonging to R2 such that. So type 2 description means y variable will going to receive constant limits. So observe your region vertically. Observe your region vertically. This is the bottommost extreme point of the region, and this is the topmost extreme point of the region. So according to y, your region lies between these 2 points. The values of y for your region lies between these 2 endpoints. So what is the value of y for this point? 0. 0 less than equal to y, less than equal. What is the value of y for this point? That's 1. 0 less than equal to y, less than equal to 1. These are the upper and lower limit for y. Now to find limits of x, you have to draw horizontal arrows parallel to x-axis pointing from left to right. Pointing from left to right. The direction is from left to right. Observe their initial point. Where are they lying? They're lying on straight line. What is the equation of straight line? Y equal to x. We want limits of which variable? Y is already done. So we are finding limits of x. So what is the value of x from this? Y. So lower limit of x is y. Lower limit of x is y. Now to find upper limit. Observe tips of all the arrows. Observe tips of all the arrows. Where are they lying? They are lying on parabola. What is the equation of parabola? Y equal to x square. We are finding limits of which variable? X. So what is the value of x from this? So solve this equation for a value of x. So from this, there are 2 values of x. X is equal to plus or minus square root of y, because we have to take the square root for the value of y. Sorry, for the value of x. Observe this part of a parabola, it lies in first quadrant. The part of parabola on which tips of all the arrows lies, that part of parabola lies in first quadrant. In first quadrant, x is always positive. So upper limit for x is positive square root of y. Upper limit for x is positive square root of y. So this is the description of the same region, but this time it's a type 2 description. It's a collection of all x comma y belonging to R2 such that 0 less than equal to y less than equal to 1 and y less than equal to x less than equal to square root of y. Y has got constant limits and x has got variable limits. And this is a type 1 description for the same region where x has got constant limits and y has got variable limits. Is it okay?
Yes, sir.
Okay. So in general, type 1 description looks like this. B is collection of all ordered pairs x comma y belonging to R2 such that a less than equal to x less than equal to b and phi of x less than equal to y less than equal to psi of x. X will receive constant limits and limits of y are functions of x. In this case, by Fibonacci theorem, general form, we can evaluate the double integral f dA over capital D by distributing limits of these two variables to these two integral sign. But this time it's not arbitrary distribution. The distribution is fixed in the sense the constant limits are always outside. So in this case, the variable x has got constant limits. So outer integral will receive limits of x. X is running from a to b. And then the inner variable will receive limits of y. Y is running from phi of x to psi of x. Then your function of integration. And then order of integration. That is also important in the sense inner integral has got limits of y. So we are going to integrate with respect to y first, and then we are going to integrate with respect to x. Suppose we have used type 2 description for the region. Suppose we have used type 2 description for the region capital D. So in this case, capital D will look like of this form. Xy belonging to R2 such that C less than equal to Y less than equal to D, and some phi 1 of X less than equal to, phi 1 of Y less than equal to X less than equal to psi 1 of Y. So in this case, the variable Y will going to receive constant limits, and the variable X will receive limits in terms of Y. They are functions of Y. So when we use the Fibonacci theorem general form and type 2 description, there are two variables and there are two integral signs. So it's not a random distribution. The constant limits are always outside and the variable limits are always inside. So outer integral will receive limits of y and the inner integral will receive limits of x. So if you use this type 2 description, the double integral will look like this. Double integral of f dA over d is y from C to D, x from phi 1 of y to psi 1 of y, then your function in order of integration. As inner integral, this has got limits of x, so we have to integrate with respect to x first, hence dx, and then dy. Afterwards, you have to integrate this to y. So this is a Fibonacci theorem general form. If you are using type 1 description, then you have to distribute the limits like this. If you are using type 2 description, then you have to distribute the limits like this. So why we have two different types? Because there are two variables, x and y, and we have a liberty whether to provide constant limits to x or constant limits to y. But at the same time, they have their own advantages. Sometimes region is like that. When you try to describe that region as a type 1 region, you may have to distribute region in several parts. But if you try to describe the same region as a type region, type 2 description, then there is no need of dividing your region. In one go, it will go off. So type 1 description has its own advantages and type 2 description has its own advantages. Now, I will move on to R3. So in R3, we have three axes, x-axis, y-axis, and z-axis. All three axes mutually perpendicular to each other, intersecting 0 of each other. This three perpendicular axis divides the space into 8 parts. Those are called as 8 octants. So important surfaces in R3, first one is plane. I hope all of you know the equation of plane is like this: ax plus by plus cz plus d equal to 0. Linear equation in 3 variables. Such an equation is the equation of a plane in R3. So if I want to plot a plane in R3, then I need to find intersection of that plane with x-axis, intersection of that plane with y-axis, intersection of that plane with z-axis. Once I have those 3 points, connect them, those 3 points, by a plane, and that is the plane, because we know from any 3 distinct points there is a unique plane. Second important object in R3 is sphere. So equation of sphere is x square plus y square plus z square is equal to r square. This is a sphere centered at origin of radius r. Centered at origin and radius r. So it looks like this, of radius r. Is it okay? Then next object is paraboloid. Like z is equal to x square plus y square. That's the equation. This is the equation of paraboloid. How does this paraboloid looks like? So it looks like this. X-axis, y-axis, and this is z-axis. And this is what it looks like. Now, if you want to visualize this equation, you have to visualize this equation in 3 coordinate planes first. For example, if I substitute y equals to 0 in this equation, that means I will left with z is equal to x square. So in xz plane, the equation looks like z is equal to x square. That is the equation of parabola. So in xz plane, it's a parabola. That means this is my x-axis and this is my z-axis. So if I'm going to observe the surface from laterally, either from left side or right side, it will looks like a parabola. If I observe the solid in yz plane, that means I will substitute value of x as 0. So I will left with the equation z is equal to y square. That means I'm observing the solid or the surface, the equation in yz plane. This is my y-axis, this is my z-axis. So I'm trying to observe the solid from front side. So from front side, it's again looks like a parabola. So laterally also it is parabola, and front and back also it is parabola. But when I substitute z is equal to 0, then I will be left with the equation x square plus y square equal to 0, which has only one point, 0, 0. So this equation intersects with xy plane only at the origin. But if I substitute some value for z, say z is equal to 1, then I am getting an equation x square plus y square equal to 1. So at a height of 1, if I try to observe, I will get a circle of radius 1. At a height of 2, that means z is equal to 2. I will again get a circle, but this time radius is square root of 2, and so on. So if you observe the region from top side, there are circles of increasing radius. If you observe the region from front side, it's a parabola. If you observe the region from left and right, it's again a parabola. So such a surface is called as paraboloid. Such a surface is called as paraboloid. Then sometimes we may come across the surfaces called as cylinders. If I consider any two variable equation in R3, like x square plus y square equal to 4. This is the equation in two variables. So in R2, it represents a circle of radius 2. In R2, it represents a circle of radius 2. But is it possible to observe same equation in R3? So answer to this question is yes. You can observe the same equation in R3. But this time, the observation will be slightly different. In the sense, in xy plane, it's a circle. So where is the xy plane here? Xy plane is a horizontal plane. So there it is a circle. And the equation doesn't involve z. Equation doesn't involve z. That means there is no bound on z. That means there is no bound on z. You are allowed to move value of z from minus infinity to plus infinity. So hold this circle and move it from minus infinity to plus infinity along z axis. So you will end up with something like this. This is called as right circular cylinder. This is called as right circular cylinder. So it depends on the equation. This equation is called as generic equation for that cylinder, and the axis is the z axis is the axis of this cylinder. At the same time, if I consider another equation like y equal to x square, then in xy plane it's a parabola, upward parabola. But I can consider the same equation in R3 also. So in xy plane it's a parabola. So here it looks like a parabola like this about y-axis. It's a parabola like this. Since this equation doesn't involve z, we are free to move along z-axis from minus infinity to plus infinity. So if I move this along z-axis from minus infinity to plus infinity, I'll end up getting some surface like this. This is called as parabolic cylinder. This is called as parabolic cylinder. So there is a mobile app which is available for the software called as Geogebra. It's a free and open source software. Since it is free, so students can also use it. There are two versions of this, Geogebra in 2D and Geogebra in 3D. So we can observe all these equations in this app in your mobile itself in R3. So let me show you those equations in R2 and R3. So this is a window of GeoGebra, which is available in mobile app. It's a 2D version. There is another app for 3D version where you have the graphical representation on the top of the window, and there is a plus sign in between below the blue line where you can actually enter any equation which you like to visualize. Say, for example, x plus y equal to 1. That's it. That's a straight line. So as soon as you enter the equation, its graph is there. You can visualize any equation like x square plus y square equal to 4. That's the equation of circle. That's the equation of circle. We already know that. Like another equation, y equal to x square. That's the equation of parabola in red. Or we can substitute like some other equation, y equal to 4 minus x square. That's a downward parabola. Y equal to 4 minus x square. That's a downward parabola. So whichever equation you can think of, you just have to enter the equation and we have the graph in front of us. So if I say my region is bounded by two lines, y equal to 4 minus x square and y equal to x. So y equal to 4 minus x square is a downward parabola and y equal to x is a line passing through origin. So at least geometrically we are able to see some bounded region. And then you have to find those two intersection points by solving those two equations simultaneously. And then you can use either type 1 description or type 2 description to describe this region. So if I use type 1 description, then that will be beneficial. There is no need of dividing my region into two parts. But if I use type 2 description, then you have to divide your region into two parts. Now let's go for R3 version. This is a 3D app for GeoGebra. Here also we can observe lots of equations like x square plus y square plus z square equal to 4. So that's a sphere. That's a sphere. It is very nicely plotted. There are three axes which are visible. Vertical is z axis and the horizontal are x and y axis. Let's go for some other equation like z equal to x square plus y square. This is the equation which we have just now seen. So if I try to observe the surface or the solid from laterally, then laterally it looks like a parabola. Laterally it looks like a parabola. But if I try to observe surface or the solid from top side, so they are increasing circles. They are increasing circles. Let's consider equation of a plane like x plus y plus z equal to 1. That's the equation of a plane. Observe this equation of a plane. See, it's a slanting plane. That plane intersects x-axis at 100, intersect y-axis at 010, and intersect z-axis at 001. And we can rotate this and we can see how the plane looks like in 3 dimension. Let's look at some other equation like equation in 2 variable, but this time in R3, like x square plus y square equal to 9. See this. So in xy plane it's a circle, but since z is absent in the equation, so there is no bound on z. There is no bound on z. So you are free to move the z along. Sorry, you are free to move that circle along z axis from minus infinity to plus infinity, and we have right circular cylinder in front of us. Similarly, we can consider another equation y equal to x square. Observe this. In xy plane, if you observe, in xy plane it's a parabola. In xy plane it's a parabola along y-axis. Y equal to x square is a parabola along y-axis. Since variable z is absent, so you are free to move that parabolic curve along z-axis from minus infinity to plus infinity. And we have the shape which looks like this is called as parabolic cylinder, which is called as parabolic cylinder. Now what happens if I permute the variable? For example, if I take z equal to x square, then it will look like this. See, z equal to x square. So in xz plane, it's a parabola. So in xz plane, it's a parabola. See, this is the xz plane. In xz plane, it's a parabola. And variable y is absent. So you are free to move along y-axis from minus infinity to plus infinity. So that's a parabolic cylinder. Similarly, whichever equation you think of, and you just have to input here. There is a smart keyboard available where you can input those equations and you have the graph right in front of you. So let's take one more equation, z square equal to x square plus plus y square. Observe this, z square equal to x square plus y square. This is the shape. This is called as right circular double nap cone. Double nap right circular cone. There are two naps because one nap is above xy plane, another nap is below xy plane, and it is right circular. The top view is like a circle. That's why it is circular. So the thing is, you can make use of these two softwares. You can make use of these two softwares in your mobile phone. Mobile phones are available to each and every student nowadays. So you can make use of these two softwares, GeoGebra in 2D as well as GeoGebra in 3D, to plot curves in R2 as well as surfaces in R3. You can draw plenty of surfaces. You can observe their intersection. You can figure out what is your bounded region. And finally, you can go for describing those regions. If you are able to imagine, then only next step is to describe that region. There is a step-by-step procedure to describe that region. So these two apps definitely will help you for visualizing the surfaces as solid region and understanding those solid region. So I will conclude my today's talk. Thank you.